Here are the answers for the section 4-4 homework. Starting on page 134 with the orals, we're asked to state the factors. This is just another way of saying factor the polynomial. In number 1, we have a binomial, 2x minus 2y. This has two terms. They're separated with a minus sign. The reason why we factor polynomials in algebra is because it's often useful to have the polynomials written as products instead of as separated terms. Factoring a polynomial means to find out what factors multiply together to create the polynomial. Factoring is a two-step process. In step 1, you try to factor a GCF. That's why in the previous section we practiced finding greatest common factors. In step 2, you look for a special pattern. In this section of the book, there are 4 different special patterns that are discussed. It'll take practice to learn those special patterns so that you recognize them when you see them. The more of these that you practice, the easier factoring becomes, and then the easier algebra problems become. Let's apply the two-step process to all the factoring problems in this homework. First, look for a greatest common factor. Is there a number that divides into this term and this term? There is. That number is 2. You write it down. Then multiply, and let's find the other factor. What is the thing that's multiplied to 2 to create this polynomial? This is a binomial, so this other factor must be a binomial. I'm going to write parentheses with enough room to have 2 terms. Then I'm going to ask myself mental questions. 2 times what makes 2x squared? And I think this needs to be an x because 2 times x creates the 2x squared term. Then I'm going to ask 2 times what makes negative 2y? I think that's negative y because 2 times negative y makes this minus 2y term. This is a product. It's 2 times x minus y, whereas this form is a sum. It's 2x plus negative 2y. These are equivalent expressions. If you perform the distributive property on this one, it creates this one over here. We can think of factoring as the opposite thing of the distributive property. The second step in factoring is to look to see if we have a special pattern. The number 2 is just a constant. Let's look at this binomial to see if it fits a pattern that was discussed in the section. It does not fit any of the 4 patterns. So we are done. Now number 3. The first step is to look for a greatest common factor. Is there anything that is a factor of the first term and it's a factor of the other one? It looks like they have the letter y in common. Write that down. Then multiply. Let's put some empty parentheses with enough space to fill in 2 terms. I know I need 2 terms in there because our original polynomial has 2 terms. Now ask yourself the mental question. Y times what makes m squared y? We need the m squared. Then ask y times what makes n squared y? We need a positive n squared. Now inspect that second factor to see if it fits one of the 4 special patterns from the section. Both terms are squared, but in the middle there's a plus sign. There was not a special pattern that fits this, so we're done. Number 7. First step, let's look for a greatest common factor. Is there anything that divides into this term and divides into this term? The only thing would be the number 1, but there's no need to write down a GCF of 1. The second step is to look to see if this fits one of the patterns that we learned, and it does. On page 133 of the book, we learned a special pattern that looked like this. A squared minus b squared is equal to a plus b times a minus c. X squared minus 49 fits that pattern, a squared minus b squared, where the letter a is the x and the letter b is the number 7. because 7 squared is 49. Once we know what pattern it fits, we can follow the directions given in that pattern. We can see that our answer has 2 sets of parentheses. It has a plus sign here and a minus sign here, and then we need to fill in the missing spots. In our question, the letter A is an X. And in our question, the letter B is the number 7. We're asking ourselves some mental questions. What times what makes x squared? And that's x times x. What times what makes negative 49? That would be positive 7 times negative 7. So here's our factored form. Number 13, step 1, look for a greatest common factor. There is no number other than 1, which divides into 9 or 100, and the variables are not in common either, so there is no GCF. Now let's look to see if this fits a special pattern, and it does. This one also fits the pattern a squared minus b squared equals a plus b times a minus b. In this polynomial, the letter a is 3a, and the letter b is a 10b, because 3a squared makes 9a squared, and 10b squared makes 100b squared. Let's follow the directions given by this pattern to get the answer. 2 sets of parentheses. Let's fill in this spot and this spot. What times what makes 9a squared? That's 3a times 3a. What times what makes negative 100b squared? That's positive 10b times negative 10b. Number 17, first step, look for a greatest common factor. There is no common factor other than 1 in both of those terms. Second step, does this fit a special pattern given in the book? And it does. It fits a pattern on page 134. The pattern is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. In our polynomial, the letter a is an r, and the letter b is a 2. What's helping me to figure these out is that I'm looking at these terms to see if they are perfect cubes. I know that r cubed is a perfect cube, but I also know that 8 is a perfect cube, because from experience I know that 8 is 2 to the 3rd power. Let's follow this pattern to get the answer. A smaller set of parentheses and a larger set of parentheses. The letter A is an R in our question. Then there's a minus sign. The letter B is a 2 in our question. Over here it says A squared. That would be an R squared. Then there's a plus sign. Now A times B. In our question, that's R times 2, which makes a 2R. Then there's a plus sign. And then it says B squared. In our question, that's 2 squared, which is a 4. Number 23, first step, look for a greatest common factor. But there is no number other than 1 that divides into all 3 terms. Second step, is it one of the special patterns? And it is. It was on page 134 of the book. A squared plus 2ab plus b squared equals a plus b squared. In our polynomial, the letter A is really a 2a, and the letter b is really the number 1. The middle term is twice the product of a and b. So 2a times 1 is 2a, and twice that is 4a, and that is what we have in our polynomial. So following this pattern, the answer has a set of parentheses, squaring on the outside, and on the inside we're going to fill in 2a plus and then 1. Number 29, look for a greatest common factor. There is no number other than 1 that divides into 16, 24, and 9. Next, look for a special pattern. The special pattern is a squared minus 2ab plus b squared is equal to a minus b squared. In our expression, the letter a is 4x, and the letter b is the number 3. 4x times 3 is 12x, twice 12x is 24x, and that is what we have in the middle. So following the pattern, the answer will have a set of parentheses, squared, then fill in the 4x, and the minus, and the 3. Page 135 says to factor, so more of those same problems. Look for a greatest common factor. Both terms divide by 2. Write that greatest common factor down and follow it up with parentheses, with enough space in there to fit however many terms we have. Now ask yourself, 2 times what number makes 2x squared? We need the x squared. 2 times what makes negative 18? We need a negative 9. You can do a quick check. 2 times x squared is 2x squared. 2 times negative 9 is negative 18. Second step, examine that factor to see if it fits a special pattern. And it does. That is the difference of squares. It fits the pattern a squared minus b squared. It's just that the a is an x in our problem, whereas the b is the number 3. So let's follow the factor rule for difference of squares. The answer will have 2 sets of parentheses, a plus b and a minus b. Let's fit that pattern to our problem. Here's the 2, then 2 sets of parentheses, x plus 3 and x minus 3. Number 3, both terms have an x in common, so you write that down and follow it up with parentheses. X times what makes x cubed? We need an x squared. X times what makes negative 4x? We need a minus 4. Now look at this binomial. Does it fit a special pattern? It does. It also is a difference of squares, where the letter a is an x and the letter b is a 2. So here's our x. 2 sets of parentheses. What times what is x squared? That would be x times x. What times what is negative 4? That would be positive 2 times negative 2. Number 5, look for a GCF, but there's not one. Now look if it fits a special pattern. This is a difference of squares. It fits the pattern a squared minus b squared. But the a is an a squared, and the b is the number 4. Let's follow our pattern that we use for difference of squares. 2 sets of parentheses. What times what makes a to the 4th? A squared times a squared. What times what makes negative 16? Positive 4 times negative 4. Let's look at these factors to see if either of them fits a special pattern. The first one does not. While these are both perfect squares, there's a plus sign in the middle, and we don't have a special pattern for that. But this one over here is a difference of squares, like we've been practicing. So the final answer will start with a squared plus 4, but then the a squared minus 4 will factor with 2 sets of parentheses. A plus 2 times a minus 2. Number 7. This one has a GCF. All the terms divide by 5. So write the 5 down and put parentheses after it that are long enough to fit however many terms we have. 5 times what makes 5a squared? We need an a squared. 5 times what makes negative 30a? We need negative 6a. 5 times what makes 45? We need a positive 9. Step 2, examine this factor. Is it one of our special patterns? It is. It fits the a squared minus 2ab plus b squared pattern, where the letter a is an a, but the letter b is the number 3. So our final answer begins with 5, and then it has a set of parentheses with squaring on the outside. Fill in the a, fill in the minus sign, and fill in the 3. Number 9. Number 9 begins with a negative leading coefficient. Let's factor out that negative, allowing us to rewrite the trinomial with a positive leading coefficient. You should use this strategy whenever you have a polynomial that begins with a negative number. Now look at the factor we created to see if it's a special pattern. And it is. This is a perfect square trinomial. That's the a squared minus 2ab plus b squared pattern. It's just the letter a is a k in this one, and the letter b is the number 18. Maybe you're wondering how I know that. I look at the first term and take the square root to figure out what value is our a. And I'm looking at the last term and taking the square root to figure out what value is the letter b. So our final answer has the negative, then one set of parentheses with squaring on the outside, and then k minus 18. Number 11. As we look at all 4 terms, there is not a greatest common factor. However, if we group the 4-term polynomial into a pair of binomials, then each of those pairs does have a GCF. Looking at the first binomial, there's an x in both terms. Let's write the GCF down, followed by a set of parentheses. X times what makes ax? We need an a. X times what makes negative bx? We need a negative b. Now look at the other set of parentheses. There's a y in common. So write down plus y, followed by a set of parentheses. Y times what makes ay? We need an a. Y times what makes negative by? We need a negative b. Be careful that you put a plus sign here in the middle because of this plus sign here in the middle. We began with a 4-term polynomial. We now have a 2-term polynomial. Here's the first term, and then after the plus sign, here's the second term. Both of those terms have a greatest common factor. That is the binomial a minus b. So write down that greatest common factor and follow it up with a set of parentheses. A minus b times what makes x a minus b? We need the x. A minus b times what makes the y a minus b? We need a positive y. Here's the factored form. The technique that we used there to factor a 4-term polynomial is called factoring by grouping. We made 2 groups, or 2 binomials. Number 13, we have a trinomial. Is there a GCF? All the terms divide by 5, so you write down 5, and then put parentheses large enough to fit a trinomial in. 5 times b squared makes 5b squared. 5 times positive 14b makes 70b. And 5 times 49 makes 245. Now inspect this trinomial. Does it fit a special pattern? And it does. It is our perfect square trinomial pattern, where in our problem, the A is actually a B, and the B is actually the number 7. To find those two values, I'm doing square roots. The square root of B squared is B. The square root of 49 is 7. The reason I need to know those two values is because they are what go in my parentheses. The B goes here, and the 7 goes here. Number 15, all the terms divide by 2. That will leave x squared minus 32x plus 256. This trinomial might be a perfect square trinomial. Let's see if it really fits this pattern. The letter A is actually an x in our problem, and the letter B is actually the number 16. X times 16 is 16x, twice 16x is 32x, and that is what's in the middle. So the final answer begins with 2. It has parentheses with squaring on the outside, and we have x minus 16. Again, the way I'm figuring out the x and the 16 is I'm doing square roots. The square root of x squared makes x. The square root of 256 makes 16. This has a minus in the middle, so this has a minus in the middle. Number 17, there's no GCF other than 1. But this does fit one of the patterns in the book. The book has it written as a cubed plus b cubed. And it tells us whenever we have that pattern that it's equal to a binomial times a trinomial. In the binomial, it's a plus b. In the trinomial, it's a squared minus ab plus b squared. It's just that in our problem, we have an m and an n instead of a and b. But we follow this pattern and we simply fill in our m and our n wherever the a and the b are. So a smaller set of parentheses and then a longer set of parentheses. This is m plus n, and then m squared minus mn plus n squared. Number 19, there's no GCF other than 1. Is this a special pattern? It is. This fits the pattern a cubed minus b cubed. In our problem, the a is 4x. The b is a 1. Now, how am I getting that? I'm looking at the original problem, and I'm noticing the cubing. So I'm going to take a cube root. The cube root of 64x cubed is 4x. The cube root of 1 is 1. The answer will have a smaller parenthesis and then a longer parenthesis. The 4x goes here, the minus sign, and the 1. Then we square the 4x to get 16x squared. We change the sign to a positive. We take the product of the two numbers, which is 4x, and then we have a positive again, and then we square the 1, which is a 1. Number 21 fits that same pattern. I look at that, I see the cubing, and it makes me wonder if that fits the difference of cubes pattern. The letter A is 3y. The letter B is a 1. So smaller parentheses, longer parentheses. 3y minus 1, and then 9y squared plus 3y plus 1. I'm getting the 9y squared from squaring this. I'm getting the 3y from timesing these together, but changing that sign to a plus. I'm getting the 1 by squaring that 1. Number 23 has 4 terms, so I'm going to think about doing grouping. In the first binomial, there's a common factor of a. Let's write that down. That's the GCF, followed by a set of parentheses. A times 3a makes 3a squared. A times negative 2x makes negative 2ax. In the other binomial, there is a negative leading coefficient. We discussed this before. You factor out a negative sign and then follow it up with parentheses. We need a 3a and then a negative 2x because negative times negative is our positive. Now we have two terms, and they have a greatest common factor. The 3a minus 2x is shared in both places. Let's write that down. That's our GCF. Then, in the other parentheses, figure out what we need. We need an a and then a minus 1. Number 25, when I see the cubing, it makes me wonder if this fits the difference of cubes pattern. The cube root of 125 is 5. The cube root of y cubed is a y. Small set of parentheses and then a longer set. Here's the 5, the minus, and the y. Squaring the 5, we get 25. Changing the sign, we get a positive. Multiplying them together, we get 5y, then a positive, and then y squared. Number 27, as soon as I see the cubing, I'm wondering if this is the difference of cubes pattern. On a calculator, find the cube root of 729. It's 9. And the cube root of 8y cubed is 2y. Small set of parentheses, longer set of parentheses. Here's the 9, the minus, and the 2y. 9 squared is 81. Change to a plus sign. Take the product of these two. That's 18y. Then a plus sign again, and square the last term. 2y squared makes 4y to the second power. Number 29. I see the minus sign, so I'm wondering if this is a difference of squares or a difference of cubes. The exponent 6 is both a perfect square and a perfect cube. Looking at 27, that is not a perfect square, but it is a perfect cube. The cube root of 27 is 3. So this fits the pattern a cubed minus b cubed, where the letter a is x squared, and the letter b is the number 3. I know it's these two things because when I take the cube root of x to the 6th, I get x squared, and the cube root of 27 is 3. Small parentheses, longer parentheses. Here's the x squared minus 3. Now let's build the trinomial. X squared squared is x to the 4th. Change the sign to plus. Take the product of the two things, 3x squared. Then a plus, and then square the 3. That makes 9. Number 31. There is no GCF, so let's look to see if it's a special pattern. As soon as I see the cubes, I wonder if it's a sum of cubes pattern. Does it fit this pattern? In our problem, the letter A would be mn squared, and the letter B would be a D. So a small set of parentheses, and then a longer set of parentheses. mn squared plus D. Then square the mn squared. We get m squared n to the 4th. Change the sign to minus. Take the product of these two terms. We have d mn squared. Then a plus. And now square the d. Number 33. There's no GCF. Is it a difference of squares or a difference of cubes? The number 1 is both a square and a cube, but when you look over here, the number 8 is a perfect cube. So I think this fits the pattern a cubed minus b cubed, where a is a 1 and b is a 2n squared. Small set of parentheses, long parentheses. Here's the 1 minus 2n squared. 1 squared makes 1, change to a plus sign, take the product of the two terms, now a plus sign, and square that, 4n to the 4th. Number 35 has 4 terms. Let's try the grouping method. In the first binomial, both terms have a common factor of a squared. A squared times a makes a cubed, and a squared times negative b makes negative a squared b. The other binomial begins with a negative, so let's factor out a negative. And then in parentheses, a minus b. Now we have 2 terms instead of 4 terms. And they both have in common an a minus b. So write down a minus b, that is the greatest common factor. Then in the other parentheses, put a squared minus and 1. A squared minus 1 is a difference of squares, so we need to factor farther. A difference of squares factors into 2 parentheses. A times a is our a squared, and positive 1 times negative 1 is the negative 1. Last, number 37. This is a difference of squares. I'm looking for the special patterns, and when I see a minus sign, I wonder if it's one of the special patterns called a difference. Then I'm looking at these exponents to see are they cubes or squares, and when I see the squares, I know it's a difference of squares. It fits this pattern from the book. It's just that the letter A is an x minus 1, and the letter B is a y. To factor a difference of squares, there are 2 sets of parentheses. What times what makes x minus 1 squared? It's x minus 1 times x minus 1. What times what makes negative y squared? It's positive y times negative y. Here's our factored form.